very first physical principle that we need to talk about for fluids is going to be Pascal's principle, a very powerful principle. Just kind of reading it off, it actually sounds pretty simple. What it says is if you apply a pressure to one side of a confined fluid, the pressure at each and every single point in that fluid is going to increase by that same amount. What that kind of means is if you have, say, a jar of toothpaste and you squeeze the bottom of it, that pressure is going to be applied everywhere in that fluid, and the toothpaste is going to be able to come out the other end. We can take advantage of this principle. We can say that if you put a pressure on one side of, say, a hydraulic lift or a hydraulic brake, that pressure on one side must be equal to the pressure on the other side. Taking a look at this hydraulic lift setup right here, these pressures are going to be, in terms of forces, we can say that the pressure on one side, the force on an input side divided by its area, force divided by area on the input side, pressure on that side must be equal to the pressure on the other side. So the force out divided by the area on the outbound side. We can then say, I'll multiply both sides by the area out, and say that the force on the output side is going to be the force on the input side multiplied by the ratio of the areas, area out divided by area in. If these areas are different, suppose the area out was 20 times larger than the area in, suppose that guy was equal to 20, then we could apply 200 pounds on the input side. That could be an input force. Then our output force would then be 200 pounds multiplied by the ratio of the areas, be 20. We can get 4,000 pounds of lifting force simply by applying a 200 pound input force. So we can lift very heavy objects with not a whole lot of effort on our part. However, in the real world, this is an example of mechanical advantage. One thing we always need to consider is the amount of work will always be the same. So essentially we need to apply this input force over a much longer distance compared to this output force, which is very large. You press a whole long distance on this side over here for just a tiny little smidgen of distance over here. The same principle applies for master cylinders on brakes. We have a large area and it gets constricted down to a smaller area, letting us apply a large force to our brake drums. So how do we measure pressure? Well, there's a lot of types of pressure gauges. The most simple is going to be this open tube manometer, or manometer. It's a measurement of manlyhood. Kidding. This is simply an open tube where we have atmospheric pressure pressing down on one side, and on the other side we apply a pressure to it. What Pascal's law says is that pressure must be distributed equally, so what's going to happen is the liquid is going to rise up until we get some pressure due to the fact that there is a differential in height from these, from the height of this liquid right here. Or height of this fluid. What we can then say is the pressure that's being applied must be equal to the atmospheric pressure on one side, in addition to the density times gravity times the differential in height that now we can measure, and we can read what that differential in height is off of a scale. So that's how we get our height differential. Right, that is going to have some pressure associated with it. Typically what we do is we choose a very dense, a very heavy liquid, such as mercury, so that way the height differential isn't very large. If we use something like water, then we're going to need a very large height differential in order to balance out pressures, but if we use something heavy like mercury, then the height differential doesn't need to be that large. So that's why we typically see another unit of pressure as being how many millimeters of mercury. That's because we would use mercury as our fluid, that would be the density, and then this height differential is going to be how many millimeters this mercury had to rise up to balance that pressure. Another pressure gauge that you're probably more familiar with is going to be this tire gauge right here. In this case, we're going to have some input pressure, and it's going to simply compress a spring that's attached to a rod. Now we know that the force of a spring is going to be K multiplied by how far it is compressed. And if we know the area right here, if we know that area, then we can work a relationship knowing the spring constant of how far this gauge is compressed is going to be related to how much pressure, and we can just simply read that off there, and it's been calibrated based on the spring constant that we know. Another funkier one is this gauge right here, which we typically don't even hardly see anymore. Nowadays we have air pressure pressing down on a piezoelectric, and we can measure the change in current in an object rather than having this weird funky little spring scale. Another type of gauge that was designed specifically to measure atmospheric pressure is going to be called the barometer. It was developed by an Italian, Torricelli, and really it was designed to measure atmospheric pressure. For this type of barometer, kind of sitting over here, we can see that we have some fluid, typically it's mercury, and it's put inside of a chamber, and the chamber has a tube sticking up. The top end of the chamber has all of the air sucked out of it, so all of the air has been evacuated. So the pressure is going to be 0, and that's going to suck the fluid up the chamber. Imagine sucking on a straw. You lower the pressure at the top of the straw, and the fluid is going to come up. On the other end of the chamber, it's just open to the air, so we're going to have atmospheric pressure pressing down on that, and the weight of all of this fluid, all of typically mercury, is going to be balanced by the pressure. So we can say that the pressure of the atmosphere is simply going to be the density of the fluid multiplied by gravity multiplied by the height. For mercury, the pressure of the atmosphere is typically balanced out by a height of 76 centimeters, or you might see 760 millimeters of mercury. That's the Hg. Why do we care about this? Well, we care about it because as the pressure of the atmosphere changes, we high pressure systems and low pressure systems, if we're interested in, say, farming, we want to know when to cut our hay. We know that when high pressure systems roll in, typically we have good weather. When low pressure systems roll in, we typically have bad weather. So as the atmospheric pressure goes up and down, so also will this height, and when we have high pressure or low pressure, we'll be able to tell it by looking at the height of that mercury. An example of extremely low pressure storms are going to be hurricanes. If this pressure starts to drop like a rock and you live near the coast of Florida, then you grab your bags and you run. This fluid doesn't always have to be mercury. Same principle applies. The atmospheric pressure will be equal to the density of whatever fluid you're using. Suppose you used water, and gravity and height. Now the density of water is much less than the density of mercury, so the height that's associated with it is going to have to be much larger because its density is much lower. The product of all three of these terms must be equal to the atmospheric pressure. So you can kind of see in this picture right here, we have an open air water barometer, and this height would have to be about 10 meters for water. So imagine looking out your window at a 30-foot barometer to measure what the pressure is going to be. The next key idea is this thing called Archimedes' principle, and this idea that we're going to have a buoyant force if you submerge an object in a fluid. we're going to work some problems with this, so a very important principle. We know that the pressure is going to increase in a fluid as you go further and further down into it. Pressure of the fluid multiplied by gravity multiplied by the depth that you're in the fluid. Now this object is going to have some physical height to it, so the pressure that's exerted at the top of the fluid is going to be different than the pressure that's exerted on the bottom of the fluid. And we know that the pressure is going to be related to the force divided by the area. So we know that the pressure at the top is going to be the density of the fluid times gravity times this height 1. The pressure at the bottom is going to be, again, the density of the fluid times gravity times height 2. And we also know that the force is going to be the pressure multiplied by the area. So this force 2 is going to be larger than force 1, so we're going to be left with some net force, some buoyant force that's going to be in the upwards direction, FB right here, and that's simply going to be force 2 minus force 1. And if I take my forces to be the pressure multiplied by the area, you can see how the book gets this density of the fluid multiplied by gravity multiplied by the area, as well as the differential heights right there. We know that the area multiplied by this height differential is also going to be the volume of the object. So very key thing to keep in mind, this is going to be the volume of the object, or the volume that's submerged. If it's partially submerged, it's just going to be the volume that's submerged. And this is going to be the density of the fluid, not the density of the object. So we can write the buoyant force, FB, as the density of the fluid multiplied by the volume of the object multiplied by gravity. Very, very key equation to have written down and have some familiarity with. We can use this to calculate how much force we must lift an object with and or when it is submerged and when it's not submerged, and we can calculate what the buoyant force would be. You know that if you've ever done chin-ups off of a diving board or something, that you're lifting an apparent weight that's much less than your weight. You can do a lot more chin-ups when you're mostly submerged in water than when you're just kind of hanging there in air. So if we take a crown and we hang off of a spring scale, we can measure its weight to be 14.7 multiplied by gravity, so many newtons. Now if we take that same crown and we dunk it in water, we're going to read an apparent weight which is much less. It would be, say, 13.4 kilograms multiplied by gravity. What's going on is if we look at the free body diagram of the crown, we still have the weight in the downwards direction, but now we have this buoyant force that I talked about on the last slide in the upwards direction. So what we can do is we can say that the apparent weight of an object must be equal to that force tension prime, that tension in the string, which is going to be the difference of the weight and the buoyant force right there. We can then write the buoyant force to be equal to the weight minus the apparent weight. So that would be 14.7 minus 13.4. Both of those multiplied by gravity are 9.8. We can then get the buoyant force. That would be 12.74 newtons. Now what we could do is we could say that the buoyant force must be equal to the density of the fluid. If we're using water, we know what that density is, multiplied by the volume of the crown multiplied by gravity, and figure out what the volume of the crown would be. Then we could take a look at the weight, which is related to the mass, and we could relate that volume using the mass to figure out what the density of the crown would be. And example 10.8 goes ahead and does that. I highly suggest you take a look at that problem and finish working it. Now, not all objects are going to stay submerged, and if an object's density is less than that of water, then the buoyant force will be larger than the weight of the object. Here you can see that the buoyant force is going to be 200 kilograms multiplied by gravity. That's the density multiplied by the volume multiplied by gravity, and the weight is simply 1200 kilograms multiplied by gravity. So there's going to be a net acceleration upwards. Once the object reaches the top of the surface, it's going to bob up and down until the buoyant force is going to be equal to the weight of the object. Now, in this case, we're going to write the buoyant force to be equal to the density of the fluid multiplied by gravity multiplied by the volume. In this case, it's going to be of the fluid that is displaced. So it's not going to be the volume of the log, which we had up here, which we had in the last page. It's going to be this volume right here, which is going to be the volume of the fluid, not necessarily the volume of the log. We can use Archimedes' principle to come up with a relationship between the densities and volumes for an object that is partially submerged. Here I have the buoyant force as I wrote it on the last page, and here we've taken the mass of the object and we've simply said that the mass of the object is going to be equal to the density of the object multiplied by its volume. So we've written the mass of the object in terms of its density and its volume. Now, if this object is floating, it's not accelerating, then this buoyant force must be equal to the weight of the object. So we can say that the density of the fluid multiplied by the volume, I'm going to say that's of the fluid here, it says displaced, and then gravity must be equal to the density of the object multiplied by the volume of the object multiplied by gravity. And we can see that gravity is going to cancel out. So we can write our ratio of the volume of the fluid, which we can often measure, as well as the volume of the object, is going to be equal to the density of the object and the density of the fluid. That's a fluid right there. Now, typically, we can measure the volume of the fluid and the volume of the object, and we very typically use water, so we know the density of the fluid, so we can very often figure out what the density of unknown objects is going to be. Something else to consider is if this density of the object is the same as that of water, so if that's equal to 1, then the object is just barely going to be under the surface. In that case, the volume of the object is going to be equal to the volume of the water displaced. If the object is half as dense, just like that, then we're going to have a situation like we see right here, where the volume of the fluid displaced is half of the volume of the object. Archimedes' principle also applies in air, remembering that air is a fluid. Here we have a hot air balloon that's going to displace a fairly large volume of air, so we're going to have a buoyant force that's going to be equal to the density of the fluid. In this case, it's going to be air multiplied by the volume of the balloon multiplied by gravity. On the downward side, or on the force coming down, let's just take a look at this guy right here. That buoyant force is going to be equal to the mass of the helium multiplied by gravity, which we could also say is going to be the density of helium multiplied by the volume of the balloon multiplied by gravity. And we know that the density of helium is going to be much less than the density of air. So what that says is this buoyant force is going to be in the upwards direction. And we could also even add a load on there, mass of the load multiplied by gravity. And as long as the as long as this side is balanced out perfectly, or is less than the buoyant force of the balloon, then the balloon is going to rise.